Hello, I want to do one more example on this unit of relativity, and I want to do a collision problem that's in your PowerPoint notes. So we're going to treat the collision relativistically, and what we have is a particle of mass m moving to the right with some initial velocity, we'll call u initial. It collides with another particle that's at rest. And what you end up with is this new composite particle that moves off with some final velocity u sub f. Okay. I'm going to solve this problem in the laboratory frame, R frame, meaning that we're stationary relative to this particle. We're stationary relative to little m. And so I want to show you the approaches to this problem. One of the things to realize is that since this problem is relativistic, the final mass in this collision, classically we would call it a completely inelastic collision, this final mass is not equal to the sum of these two masses in the relativistic case. If gamma sub u approaches 1, then yeah, the mass of the composite particle is equal to the sum of the masses of little m and big M. Okay, so I want to show you two different approaches to solve this problem. And in all these problems, you have to conserve energy and you have to conserve momentum. So in every case that we do involving collisions, we have to say the sum of the initial momenta the sum of the initial momenta of all the particles before has to be equal to the sum of the momenta afterwards. Let me relabel this. Okay. So you end up with what you started with. Also, the total energy is conserved. Remember, when we're doing relativistic collisions, we're conserving total energy, not kinetic energy. Whether the collision's inelastic or elastic, in the classical sense, we're conserving total energy. When you did these problems in Physics 205 in the classical mechanics course, when you use the two equations, you can only use it for elastic collisions because in the elastic collision, kinetic energy was conserved. So we're conserving total energy here. Okay? So the sum of the energies before, and I'm using the little i's as a subscript because we're summing over all the particles, equal the sum of the energies. Maybe I'll use J here. Okay, I'll use J here like I did up there. Okay, so that's what we're going to use. Momentum before equals momentum afterwards. Energy before equals energy afterwards. That's the way we're going to approach the problem. Okay? It's just that we have to write the expression for momentum and energy a little bit differently here. So I'm going to show you two different methods because, and it's because of the way we write energy. We can write the total energy two different ways, and I showed you in class how we do it. And so I'm gonna go through the two different methods. And one method will be more advantageous to the other. It just depends on what you're solving for. So let's look at method one. For method one, what I'm going to do is, well, first I'm going to conserve momentum, okay? And this one is not going to change in the two methods. So this is my picture of the collision process. My total initial momentum is the momentum of the little particle, or little m. And my final momentum is the momentum of the composite particle. Since big M was not moving, then the momentum of little m has to be equal to the momentum of big M. So I can write down P sub m, or P sub little m initial, equals P sub big M final. Or I can write it this way. I can say this is equal to, I can write it as gamma sub u initial, mu initial, equals gamma u final, our final composite mass, times our final composite, or the final speed of our composite particle. So I can write it either way. So I'll leave those as is. And then the energy, I want to write whatever I had before equals to whatever I had afterwards. No, initially, my total initial energy is going to be the total energy of little m plus the total energy of big M. Now, big M was not moving. Little m was moving. And we can write the total energy a couple different ways. If you remember, we can write the total energy in the following way. So let me write it this way first. Okay, so I'm going to write the total energy of each particle this way. So the total energy of little m can be written this way. I'll just write PM initial. So this is the initial momentum of the little particle m. And then big M doesn't have any initial momentum, so basically all you have is rest mass, or rest energy. And then afterwards what you have is the total energy of the composite particle. So that's going to be P sub m final. And then times C, and then the whole thing squared, plus the rest energy of the composite particle. And this thing squared to the 1/2. Now when I do it this way, I can solve for my final mass actually fairly quick. Well, not fairly quickly. It's going to take a little bit of algebra. So really I have two unknowns here. I have the final momentum of the composite particle as an unknown, although really it's equal to the initial momentum of the system. And I have the final mass of the system. So one thing I can do is over here, I can substitute the initial momentum of the system in here, because I know that the momentum of this object, little m, is going to be equal to the momentum of the final composite particle. And so I'll get this final expression. So just give me a moment to write this out. I know it looks a little nasty. So this equation, which is rather long, has just one unknown in it, the final mass of the system. So conceivably, I can solve for the final mass of the system. Now the question asks for the final speed of the system. So it's actually going to take me some work to solve for this, because I'm going to have to square this equation. But when I square this equation, I'm still going to have a term with a radical in it. I'm going to have to isolate the radical term and then square the whole thing again, and then solve for m final, which is going to be a lot of work. Once I get m final, then I have to go back up here into the top equation and then solve for the final velocity of the particle. So it is a lot of work to do the problem this way, but you can do it. For problems where you're just solving for the final momenta, especially for problems where you're dealing with photons don't have a rest mass, you'll probably want to solve it this way. However, you can see that if we're going to solve for u final, because that's what we're asked for in this problem that you see on the screen, this is going to take a lot of work. Because first I got to find m final, which is going to take a lot of algebra. And then I got to put that back up into this momentum equation and then solve for u final. I'm not going to do it that way. So method one can be useful in some problems, but for this particular problem, I think it's going to be a challenge for us to actually complete the problem. So I'm not going to use this method. I wanted to show you that this is an alternative method to solve problems. And again, if you're just solving for the value of p, this would be a good method to use. So let me show you the second method. And the only thing that's going to change is the energy equation. The momentum equation is not going to change. And in fact, let me erase everything, because now I have to do a little bit of algebra. And you'll see, using this method, I will do very little algebra. Whereas the other method is going to require me to use a lot of algebra. One of the questions on a practice test, it's one of the extra practice problems is going to allow you, you're going to have to use the first method to solve it. Okay, so let's do method two. Okay, so method two, I'm still going to have Pm initial, or if you want, this is the momentum, the initial momentum of little mass m equals the final momentum of the composite particle. And again, I'll write it as gamma u initial m u initial equals gamma u final m final u final. Okay? Now, the energy equation, we're going to conserve energy, and I'm going to write your basic total energy equation. So the total energy of little m, I'm just going to write it as gamma sub u initial times the rest energy of the particle. Now, since the larger particle, big M, is initially at rest, the gamma associated with this particle is 1. It's at rest. So all I have is the rest mass, or the rest energy. And that's got to be equal to the total energy of our composite particle after the collision. So I have those two equations, two unknowns. And what I'm going to do now is solve them simultaneously. And you'll see I can get u final really quick. I can get u final very quickly. So let me take the first equation. Let me take this equation. So take equation A. So use equation A. solve for gamma sub u final. Let's do that. So I'm going to solve this top equation for gamma u final. So what do I get? I'm going to get gamma sub u final is equal to gamma sub u initial, the initial mass of the little particle m, u sub I, over m final, u final. Then substitute this expression for gamma sub u final. So let's do that. And now I want to be careful not to make an algebra error. Oh, I forgot my m final. So I made the substitution for u final. Now, the m finals on the right-hand side cancel. And let me rewrite this as gamma u initial, little m, u initial over u final times c squared. Now this term has a c squared, this term has a c squared, that term has a c squared. So I'm going to cancel them out. I'm running out of space on my board, so I'm just going to cancel them out instead of rewriting everything. Okay, well, I will rewrite anyway. So what we'll get is this. Gamma sub u initial times little m plus big M equals gamma u initial, little m, u initial, over u final. My goal is to solve for u final. This is going to be easy, because all I have to do is multiply both sides by u final, and then divide by both sides by what I've just put in brackets here. So u final ends up being gamma u initial times m times u initial over gamma u initial m plus big M. And that's our final expression. And if you want, you can solve for m final. You can solve for m final if you wanted to. Okay, you'll get a more complicated expression. And it's still easier to do it this method than the other method. If we try to do it using method 1, it would be much more complicated in terms of the algebra. I mean, again, the process is the same. It's just the algebra is more nasty. Now, what happens if gamma goes towards 1? In other words, what if the speed of little m is small compared to the speed of light? Well, that would make these gammas 1. So let me erase the board here. So as gamma sub u initial approaches 1, then u final approaches m initial times u initial over the sum of the masses. So let me rephrase that. It's m times u initial over the sum of the two masses that you have initially. which is the classical expression. This is the classical expression for a completely inelastic collision between two particles, which you've done in your previous physics course. Now, if you solve for big M final, then as gamma U initial goes to 1, then M final should approach little m plus big M. If you actually went through and solved for M final, which I'm not going to do here because it's going to take a little bit of work. Okay? So your answer should reduce down to the classical expression. One fun thing you can try, and we have it in our notes, is to solve for M final, but do it in the frame of the moving particle. You can try to solve for M final in the frame of moving particle. Whether you do it in the frame of the moving particle or not, M final has to be the same because that's the rest mass of the object. Okay, I guess that's it.